G'day, Mike back, and carrying on from the even and odd function part. I hate to break the bad news to you, but most functions are neither even nor odd. That's the bad news. The good news is that every function subject to small condition on the domain can be split into even and odd parts, and that's what we're talking about today. So we still need this constraint, as we talked about when we talked about even and odd, that to be able to consider these symmetry properties, we need x being in the domain of the function is equivalent to saying minus x is in the domain. So if x is in, minus x is, and vice versa. Let's use this nice notation. Let's just, if we have an even function, we'll just use e of x for even. We have odd function, we'll use O of x. Sounds good? Okay, so let's take some simple example. So what are the even and odd parts of this very simple quadratic? Okay, so remember when we talked about even functions, we said a function is even if and only if it can be written as a function of x squared. And so this would lead us to make the assignment that the even part is equal to 1 plus x squared. So this is a function of x squared, so it's even. Well, to be able to say that that's the even part, we better have that the other part, the leftover, is odd. So the leftover part, so once you get rid of the 1 plus x squared from the 1 plus x squared, leaves us with x. Let's say that's the odd part. Well, that would be a correct statement if it's truly odd. Well, O of minus x is just equal to minus x, which is equal to minus O of x, because with this assignment, this is just equal to x, so this is indeed odd. So our simple polynomial quadratic is divided in this way into even and odd parts. So here are some natural questions that beg to be answered. How did we know that this decomposition was unique? Just because we divided it into an even and odd function, how can we say these are the parts? There are no other decompositions in this additive way. Another question would be, well, if that was a very simple function, what would the even and odd parts be for a more general function? Something that wasn't just a simple quadratic. Well, these questions are answered by the following theorem, which is fairly easy to prove, but we'll defer the proof to the details. So suppose that f is a function, so from some domain to the real line, where the domain satisfies this necessary condition for these symmetry properties. That x is in the domain implies minus x is in the domain. Then there is a unique decomposition. F of x is e of x, the even part, plus O of x, the odd part. So into the sum of this even and odd functions. Moreover, the value of e of x is just equal to f of x plus f of minus x over 2. And the value of the odd part is equal to f of x minus f of minus x over 2. Okay, we're not going to get into this proof, but let's just verify this little part here. Okay, so if you added e of x plus O of x, then what you would get is you would get f of x plus f of minus x. That would be, and then it's all going to be over 2. And then you would get plus another f of x, so that first two terms are from the even part, and then you're going to get a minus f of minus x. And this is going to cancel with this, and then you're going to have two f of x's, so this, of course, is equal to f of x. So it looks plausible, and the proof is actually relatively simple, but let's defer it. Instead, let's take some examples. So we have this example of a little bit more interesting polynomial. So this is a 5th degree polynomial. The first thing that we might do is let's guess. Okay, so we know that even functions are functions of x squared, And we also know even functions that are polynomials correspond to the polynomials with even powers. And so we would naturally guess that the even part would have this minus x to the fourth, and it would also have this minus x squared, and it would also have this minus 6. So that's what we would guess, that those three terms would be in the even part, and we guess the other three terms would be in the odd part. Let's see if that's right. So the even part by this theorem's formula is f of x plus f of minus x over 2. So it's kind of laborious, but let's just write that. So f of x, so that's going to correspond to these terms. So it's going to be x to the 5 minus 2x to the 4 plus 3x cubed minus 4x squared plus 5x minus 6. So this part here comes from the f of x. But then we have f of minus x. So now we have to substitute in minus x every time we have an x. And so we're going to get these, all of these terms over here. And then what we do is we just evaluate it. So minus x to the 5, well, that's minus x times minus x times minus x times minus x times minus x. Well, those minuses cancel out except for one of them. So you get minus x to the 5. And then minus 2 minus x to the 4th. Well, there's going to be a minus 1, minus 1, minus 1, minus 1. There's going to be 4 of them. They're all going to cancel out. So you're just going to get minus x to the 4. Similarly, this 3 times minus x cubed corresponds to minus 3x cubed. And minus 4 times minus x squared corresponds to minus 4x squared, and these other terms correspond. And now we've written all this out, and we've just copied this part down, and so now we can look at, well, what cancels. And so what cancels is this x to the 5 cancels with this minus x to the 5. This 3x to the cube cancels with this minus 3x to the cube. This 5x cancels with this minus 5x. And so we're left with minus 2 to the x to the 4, minus 4x squared, minus 6, minus another 2 to the x to the 4, minus 4x squared, minus 6, all divided by 2. Well, we have 2 of each of these. We have 2 of these, and we have 2 of these. We have 2 of these. And so this 2 is just going to cancel with each of them, and we're going to have minus 2x to the 4, minus 4x squared, minus 6. So that's the even part. Well, the odd part, we have now a choice. We could go back to this formula here, and we could use this, or else we could use this underlying formula here. And we could just say, well, O of x is equal to f of x minus e of x. Let's do the latter one. So then O of x is equal to f of x, which is this whole polynomial, minus e of x. So if we go back here, we're just going to be getting rid of these underlying terms. So this is going to get rid of these. And we're just going to be left with the rest. So it's going to give us x to the 5th plus 3x cubed plus 5x. And that's the odd part. All right, let's take a little more interesting example. Find the even and odd parts of f of x is equal to x plus 1 over x minus 2. And for this, because this doesn't have such a wonderful domain, right? So the domain of this is all points where x is not 2. So it's a real line other than 2. But let's take a domain which is just minus 2 to 2. So we have to avoid the point 2. And so let's find the even and odd parts of f on this domain. So we restricted this domain to avoid the singularity, which is at 2. So if you plug x is equal to 2 into this denominator, you get 0, so you have a singularity, you have a blow-up. Yet we still have to have this property. So if x is in the domain, then minus x is in the domain. But that's clearly true. So you pick, say, 1 minus 1 is in, right? A half minus 1/2 is in. So this is still clearly true with this domain. Hence we picked it that way. So now we just take the even part. So let's just go back to this formula for the even part. So this is the formula we're going to use, that is f of x plus f of minus x divided by 2. So let's just do that. So f of x is x plus 1 over x minus 2 plus f of minus x. So we just substitute minus x in. So we're going to have 1 minus x here, and on the bottom we're going to have minus x minus 2. And then we've got to divide that by 2. All right, so if we look at this, then let's just write this part here as, let's just write this little piece here, just for simplicity, as x minus 1 over x plus 2. So we're just canceling a minus 1 from the top and the bottom part of just that piece. And then we can find a common denominator. So this denominator that we found that's common, this is 2 times x minus 2 times x plus 2. So we found that, so we got to have this part in there, we got to have this part in there, and we got to have, well, really this part here in there. So that's why we wrote it in that way. So now when we standardize this to the same common denominator, this x plus 1, it has 2 times x minus 2, but it's missing the x plus 2. So we have to have an x plus 1 times x plus 2 here. And then we add, and now we have this x minus 1 from that part, but it's missing this x minus 2. So we bring in the x minus 2 here. All right, so then we just expand this. So x times x is x squared. Then we have 1x plus another 2x. So we have 3x plus 2. And then over here, we're going to have x squared minus an x minus another 2x minus 3x. Then minus 1 times minus 2 is plus 2. So we're going to have that. And we just multiplied the 2 in this denominator. So this is what we're going to have. And then what we can see is this 3x here is going to cancel with this minus 3x. So we're going to be left with 2 times x squared plus 4. So we can factor 2 out. So this then we could simply write this as this is equal to 2x squared plus 4. And then this would be over 2x squared minus 8. So we factor 2 from the top and the bottom, and we're left with x squared plus 2 over x squared minus 4. So that's the even part. And we can repeat this process essentially exactly the same, except for instead of this plus for the even part, we have minus f of minus x. So if we do this, but we subtract instead of add, we repeat all of these steps just as we did, we'd find that the odd part is 3x over x squared minus 4. And now we should check, is this even part plus this odd part equal to the function? Well, let's just check. So they have the same denominator, x squared minus 4 in both cases. So from the even part, we have the x squared and 2. And then from the odd part, we have the 3x. So we have those 3 parts on the top. We can factor that. The top is x plus 2 times x plus 1. And the denominator, this is factors into x plus 2 times x minus 2. And the x's plus 2's cancel. Remember, we're only worried in the domain from minus 2 to 2. So that's not 0. And so we get back x plus 1 over x minus 2, which is our function that we started with. So it's f of x. And we're done. We have our even and odd parts of this function. Here's a simple fact. So there's a lot of simple facts that can come from here. Here's one of the nice ones. A function is even if and only if it is equal to its even part. Okay, so that's another test you could do. And this also reads, a function is odd in brackets if and only if it's equal to its odd part. Thank you.